All right. Good morning, everybody. Hold on 1 second here. I apologize about yesterday. Um, yeah, I just can't figure out. Sometimes it happens, and you've already experienced it a couple times already, where I just have issues with the Edpuzzle. Fingers crossed. I hope today's lesson will upload. And so let's go ahead then and let's get started. What I'd like to do then is I'd like to get done, and so I was hoping to get started with Vesper theory on Wednesday, yesterday, so that we can do the FET lab today. But you know what I'm going to try to do for tomorrow, for Friday, try to plan the FET lab for tomorrow. But tomorrow's lesson, so we don't have we won't meet to take roll because it's a in-service day for us, and the seniors have their prayer service on tomorrow. But I will post a video. I will post a video. We do have to keep going on with this, and so hopefully with today's video, we can get started into the localized electron model where we talk about molecular orbitals, and then hopefully on Monday, fingers crossed, then we'll be able to cover and talk about the valence Vesper theory, which is valence shell electron pair repulsion theory, and we'll talk about that, and then we'll try to wrap it up. So we'll do that lab on Tuesday then. Okay, so please make sure we're going to try to work towards that, and we're going to see if we can get this material covered. Okay. All right, let's go ahead then and let's pick up where we left off with on Monday, and that was with the discussion. I'm sorry, Tuesday, and that was with the discussion of what this bond dissociation energy is and what we use it for. Okay, so bond dissociation energy is just the energy needed to break a bond. The energy needed to break a bond. That's as simple as we can state it. And so let me go ahead and share my screen here with you, and let's take a look at some bond energies here for certain bonds. Okay? And so if you take a look at the bond energies here, you're going to notice then that each bond then will have a different bond energy. Okay? Each type of bond will have a different bond energy. Okay, so if you take a look at the oxygen-oxygen double bond versus the oxygen-oxygen single bond here, so the oxygen-oxygen, this double bond here versus the single bond between two oxygens, you notice then that their bond strengths are different. The bond strength is just another way that we can describe then bond energy. Okay, and so the bond energy here is greater, which means that it's harder to break this bond. That's why we refer to it also as bond strength. So it takes about 498 kilojoules per mole of energy to break this double bond here, and only about the half of that, more than half of that, to break this single bond here, which I think makes a little bit of sense. If you think about it, you have twice as much bonding here as here. So the bond energy is not twice as much, but the idea that you have more bonds here to break, so it's going to take more bond energy. And if you think about it in that way, you can see then why this triple bond here between two nitrogens is much, much greater in terms of its bond energy than the single bond here between two nitrogens. Okay? And so the more bonds there are, okay, the more energy it'll take to break those bonds. So a single bond, it takes less energy to break than a double bond, and a double bond will take less energy to break than a triple bond. So that is generally true. But what we also have to look at then is what type of atoms are being held together. Because if you notice here, if you look at the oxygen-oxygen single bond and the nitrogen-nitrogen single bond, both of these are single bonds. But if you notice here, the oxygen-oxygen single bond here is a little weaker than the nitrogen-nitrogen single bond. So the bond strength, that is this bond dissociation energy, is dependent on two factors. The type of covalent bond that is holding the atoms together. Is it a single, a double, or triple? And the atoms that are held together by that particular type of bond. Okay? And so those two factors determine the bond energy. Okay? Now, with that said, why do we need the bond energy? The bond energy then is one piece of empirical data that we can use to support our structures. So when we drew out and when we drew the structures for diatomic oxygen here, or molecular oxygen, we said then that the only way both of those oxygens can achieve their octet and thus be stable, and we can count them here. And I'm sorry, let me just make sure I point out to you, remember these lines, I was telling you about these dashed lines here. So from now on, we will be drawing the bonds as dashed lines, okay? And so a single bond, then one dash line, a double bond, two dash lines, a triple bond, three dash lines. And so therefore, what you want to make sure you remember then is a single bond here. One dashed line represents 2 electrons. That is a pair of electrons that are being shared between these 2 oxygens. A double bond here, then we have 4 electrons that are being shared between these 2 atoms. And then finally, a triple bond here, which has 3 dashed lines here. This represents then 6 electrons that are being shared between those 2 atoms. And here again, we have another single bond. So there are 2 electrons that are being shared by 2 nitrogen atoms. Okay? So from here on out, I'm actually going to be drawing the structures like that from now on. But if you notice, then we still leave in the dots that represent the lone pairs. So with the lone pairs here, don't forget to draw the lone pairs for the for all of these atoms here. They will play a crucial role, like I told you, when we start talking about electron geometry. So I've drawn, we leave in the lone pairs as dots. It's just now the bonds now are going to be called dash. We're going to draw them as dash lines. Okay, so these then, if you can imagine, then these are what we refer to then as bonding electrons or bonding pairs. If we're going to, and this is how we'll be referring to when we do VSEPR, we'll be referring to these electrons here as bonding pairs, these electrons here as lone pairs. So 2 different types of pairings that you want to make sure you keep in mind. Okay. All right. So with that said, then what I want to make sure you understand that is, and as we go through this, when we draw, we drew the Lewis dot structure here. We saw then that it required 2 pairs, that is 4 electrons, in order for these both these oxygens to achieve their rate. So we can just quickly count it, and we see then we have 2, 4, 6, 8. This atom has 8 electrons, and this atom has 8 electrons as well. And so we need confirmation of that. I mean, the Lewis dot structure itself makes sense in terms of the logic that that I've introduced to you, but logic alone can't support what we've drawn here. Okay, we need empirical data, and that's where this comes from right there. We can measure this. This is a measured value. We also have what's called mass spectroscopy. We have what's called spectroscopic techniques. This is basically using energy to try to find out, and it is using energy, different types of energy, to find out the structure of these molecules as well. Okay, all right. So we saw that here, and we saw that with hydrogen peroxide here. Okay, a single bond between these 2 oxygens also allows both of these oxygens to obtain their octet, but in a different manner. So we need a double bond here so that both oxygens can achieve their octet. In this molecule here of hydrogen peroxide, we only needed a single bond. And so again, we need empirical data. We need empirical evidence to show that this is a single bond here, and we can get that from the bond dissociation energy. Okay. Now, if you notice here, bond length is also different for these here, and the bond length is just a little bit more. It's a little bit more difficult to obtain, but we can obtain it. And once we obtain it, then we can also use this information here to support our structures here. So if you notice, then with the bond, with the double bond here, it's a little bit shorter. The bond length is a little bit shorter than the single bond. And if you notice, then with the triple bond, it is even shorter than the double bond. So the order of bond length then is kind of what we have here. Okay, so what we have is what we have. Let me go ahead and write this here now. Summarize this for you. Okay. So with that said, then in terms of bond length, okay, and this is, remember, not only we have to consider the atoms that are held together as well, and in terms of bond energies, okay, if we were to kind of look at it generally here, okay, you would have then a single bond, okay, to a double bond to a triple bond, where length increases as we go down. So it increases as we go down. So therefore, I'm sorry, decreases as we go down, sorry. That decreases as we go down. Okay, so that the triple bond is the shortest of the bonds. In terms of bond energies then, if we take a look at this then, it's going to be then triple bond, okay, to a double bond, and then a single bond, where the bond energies also decrease here as we go down. So that means then the single bond is the weakest decrease of those bonds. Okay. All right. So that's how we can use bond length, bond energy. But then again, remember, I just pointed out to them the types of atoms that are going to be held together will also determine the differences in length and in strength. Okay. All right. So let me go ahead and share with you. So let me go ahead and save this here and share with you the table that lists for us bond strength here. Okay. So let me go ahead and let's take a look at the next table here. So here I give you a list of different bonds here. Okay. I give you the list of different bonds and their bond energies here. And so what I'd like to do then is I'm going to go ahead and use this table here to show you how we would use this information to support the structures that we have. Okay. All right, so let me go ahead, and we had two structures. We did sulfur dioxide. I'm sorry, the sulfite ion. So let's go ahead then, and I'm going to go ahead and share with you the two separate valid structures that we came up with for sulfur sulfite. Okay, so sulfite is SO2 minus. Okay, so for the very first one then, okay, for the first one then, the first structure we had then, we had sulfur as the center atom, okay, with 3 single bonded oxygens. Okay, I'm going to draw one of them, two of them separately. Okay, and then we had so those are the electrons there, and then we had 2 extra electrons come in, so it's a sulfite ion, so that I'm going to draw them in blue. Okay, and so that's where the negative charge comes from. If you take a look at it this way, then we see then that all atoms, each atom here, oxygen has its 8 electrons. Each oxygen atom will have its 8 electrons here, and the sulfur will also have its 8. Now, the other thing we can do to check to make sure that we have the correct structures then is that we want to make sure then that we count all the valence electrons. So we have to be able to account for all the valence electrons again afterwards. You got to total them. So this is what I mean here. Let me go ahead and let me show you what I mean here. So we have one sulfur. Sulfur to start out with then had 6 electrons. So the valence electrons, we have 6 total electrons for sulfur. Okay. Each oxygen will also have 6 valence electrons, and we have 3 of them. Okay, so there's our third one right there. Okay, so in total, each one of these atoms here contributes 6, so we should have a total of 24 electrons as we count the structure. However, remember, we had to add in 2 more electrons that came from elsewhere. So our structure should have a total of 26 electrons. Now, this counting of electrons here, you got to make sure you do as we move forward from here on out. Okay, so let's go ahead and make sure we count this. We have 1, 2, 3, 4. Each one of the oxygens has 4 electron pairs. Okay, so we have 1, 2, 3, 4. 1, 2, 3, 4. That's 1, 2, 3. So we have then 2, 4, 6, 8. Okay, so we have 8 electrons in each. So that's 3, 4 would be 24. Okay, 8 times 3 is 24. And then these 2 extra as well. So therefore, then yes, our structure has 26 electrons as well. Okay, so the validity of this structure is supported in 2 ways, at least. Okay, that each atom then has their 8 valence electrons, and then when you add all the atoms that are here, remember, add up the bonding and lone pair electrons, we end up with 26 electrons, which is the total amount of electrons that we expect to have in the first place. Okay. All right, so that was one valid structure that we had. Okay, the second valid structure that we drew for this compound, I think most of you hopefully got that, but the second valid structure that we got for this compound involved sulfur again being tied to an oxygen. This time, though, the 2 oxygens here are bound together. Okay, and I'm going to go ahead and I'm going to draw it this way is here. Okay, and again, 2 extra electrons that have to come in, and I'm going to draw one here, and the last one here. Now, with that said, then I think hopefully if everyone sees this, this is also valid. You have 8 electrons here, 8 electrons here, 8 electrons here, and 8 electrons here. Okay, and if you count these atoms and count up all the electrons, this also will give us a total of 26 electrons. Okay, so we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 right there. So we have a total of 26 electrons that are accounted for as well. So both of these based simply on the drawing, based on simply what we say with the octet rule, everything seems to work. So it's not. Which one of these structures is the correct structure for sulfite? So this is where then we will have to rely on bond dissociation energy here. Okay? If you notice in this structure here, we have three equivalent. We refer to it as equivalent. I'm going to go ahead and write this down. So we have then three equivalent SO bonds. Okay, so we have three single bonded sulfur oxygen. Here we have two SO bonds, S single bond, and then we have one oxygen bond. That's what we see with this structure here. Okay. What we notice when we run the energy test for this is that we have then, and this is what we see. We see then that we have the bond energy that is roughly about 260, about 700 kilojoules per mole. Okay, let me go ahead. We have then a total of 7. Let me just check my math really quickly. Just make sure I got this right. Okay. We have a total bond energy here of 795. So we have then a bond energy of 795, and hopefully you can see where that comes from. 3 SO bonds, okay? Each SO bond, sulfur oxygen, single bond here is 265. So therefore, the total bond energy that we should expect here, okay, the total bond energy that we should expect here is going to be about 795 kilojoules per mole. And that's what we see here. On this end here, we have 2, and let me check it, 2 times 265, okay, plus 1 oxygen double bond, which is 204 here. We should expect on this side here a total bond energy of 734 kilojoules per mole. Okay, all right. So you run it, and what do we notice? What do we see then? That the total bond energy comes really, really close to this right here. It comes close to 795 kilojoules. And so therefore, what can we say then? This structure of sulfite then has 3 SO single bonded atoms, SO single bonds, rather than 2 and 1 oxygen. That is how we use bond dissociation energy in order then to determine then which structure is valid here. Okay, so that's the importance of bond energy, folks. And so please make sure you understand that. And this is something that we do much more of as you get into AP chemistry. For those of you who will be moving on, but this is what we use bond energies for. Okay, all right. All right, so with that said, then let's continue on, and I want to just talk about this concept of resonance here with the time resonance. Try to get through this. We're not going to spend too much time in this here, but we've been talking about the equivalent structures. We said then that sulfite has 2 structures. Okay, I'm sorry, not equivalent. We have 2 valid structures. Okay, we have 2 valid structures. Okay. With resonance, we are faced with another problem here, and that is we have then structures that are not only valid, all of the structures are valid. So what resonance is basically saying then is that you take a molecule, okay, you draw out the Lewis dot structure to all those molecules, and then you have then every single molecule is valid in terms of the bond energies. Octet rule, valid in terms of the connections, okay? And then also valid in terms of bond energies. Okay? And so we have an issue here. And so resonance then represents then a phenomenon that we described then as having equivalent structures. So let me just quickly share with you. Let's draw the Lewis dot structure here for ozone. Okay? Ozone is that molecule that we find in the atmosphere that protects us from UV rays, but also ozone is a byproduct of combustion of gasoline as well. Okay, so let's go ahead and let's take draw the structure for ozone. I'm going to draw the puzzle pieces here really quickly to show you then what I want us to do from here on out to help us. Okay, so ozone then has 3 oxygens, 1, 2, 3, 4, 5, 6. This has 6 electrons. Okay, This oxygen also has the exact same structure, which means that it also has 6 valence electrons. And finally, the third one, okay, has 6 valence electrons as well. So we have to account for a total of 18 electrons in our structure. Okay. All right. So piecing this together here, let's go ahead and do this here. So I'm going to put one of these oxygens in the middle. Okay, so we have that. Okay. I'm going to draw the next electron, next oxygen, just right next to it. Okay. And so hopefully you see then that we have that double bond forming right there. And then the third oxygen, I'm going to write it this way here, where we have a coordinate covalent bond forming there. So the structure that I've drawn for you then has a double bond between two of the oxygens and a single bond between the third oxygen, okay, and the center oxygen as well. So drawing in the Lewis dot structures for each one of these. Let's make sure that we have a total of 18 electrons. Okay, so we have then 2, 4, 6, 8, 10, 12, 14, 16, 18. This structure here seems to be the correct structure for ozone. Okay, so this seems to be the correct structure for ozone right there. Okay. Now, the problem that we have, and this is that I want to, let me just get my table again really quickly to point this out. Okay. The problem that we have, what we should observe then right here then is if we total up the bond energies, that's an oxygen single bond, okay, which has a bond dissociation energy of 204 kilojoules per mole. Okay, and then we have this bond here, which is a double oxygen double bond, which has a bond energy of 498 kilojoules per mole. And so we add those two up, and let me just check my math again really quickly again. So we add those two up, we have then let's go ahead, 204 plus 498. We should expect then a total bond energy of 702 kilojoules per mole. That's exactly what we just did for sulfide. Okay, that's what we expect for this structure of ozone. Okay. Actually, what we find then is that the total bond energy, this is the total bond energy. Okay. What we see there with the total bond energy is that it is less. So whatever the actual total, so I'm right here, actual total bond energy for ozone is less than 702. It is less than 702 kilojoules per mole. So we sit there and we scratch our head and we ask ourselves, so what's going on here? Okay. What's going on here? Why is that less than 702? Well, the reason why then is, let me go ahead then, is that actually there is another structure that is equally valid here. And so let's go ahead and draw it. And I'm going to draw this here, okay, this arrow here. And we can draw the structure this way, okay, where we have then this oxygen on the left forms a double bond with the center oxygen, which then forms a single bond with the oxygen on the right. Okay. Now you look at this and say, wait, Mr. N, you're cheating right there, because all you did was flip the molecule around. As you take this molecule and then you flipped it over. No, it isn't the case. These are all three different oxygens, and I want to make sure I label this for you. Okay. So we have then, I'll call this oxygen number 1, oxygen number 2, and oxygen number 3. In the first molecule, the single bond is between oxygen 1 and 2, the double bond between oxygen 2 and 3. This is oxygen 1, that's oxygen 2, and that's oxygen 3. This time, the double bond is between oxygen 1 and 2, and the single bond is between oxygen 2 and 3. They're not the same structure because the bonds are not connected. The atoms are not connected in the same way. But both of them are equally valid. Both of them we should expect in a bond energy of 702. And so which one of these is the correct structure? So which one of these is the correct structure? We say then, by using this theory of resonance, okay, and resonance is the localized electron model, which I'll talk about now at this point. We'll probably talk about it tomorrow on Friday's video. But the localized electron model then states that these two are the same structure. They're the resonance structure. Okay. That means then what the actual ozone molecule is doing is that it's flipping, it's switching between both of these. You can say then that ozone has a split personality, I guess, and it's moving between both of these structures here, where part of the time you have the double bond between the second and third oxygen, and the other part of the time you have the oxygen between the first and second, the double bond between the first and second oxygen. Now that's a very simplistic way of saying it. More accurate way of saying it then is that actually the structure that exists, the structure that the actual structure of ozone is not quite either one of these at all. It's not quite either one of those at all. And that actually the structure of ozone, and let me go ahead and draw it here for you. The structure of ozone lies, whoops, sorry, lies somewhere in between. So let me go ahead and draw the structure up here. And the way that we represent that is this. Okay, so we have then 3 oxygens, okay, with a structure in which here. Okay, in which the bonding between them, okay, is partly single bonded, partly partly double bonded. And that's what resonance is. And actually, I'll come back to this in just a moment. So this bond here and this bond here is part double bond, okay, part single bond. And actually, the bond energies support that. And that is the bond energy for this bond, for these 2 bonds here, is somewhere in between 204 kilojoules and 498 kilojoules. And that's what we observe right there. And so that the bond energy then ends up being slightly less than 702 or less than 702 kilojoules per mole. Okay. Now, so that's one way we can represent it here. But the other way we can represent it is by drawing both of these structures here and drawing exactly what I did there is with the arrow between them, and showing that the molecule itself of ozone kind of flips between both of those. Okay, all right. So that's resonance. Resonance is a very important concept that we learn about moving forward as you go on to higher level chemistry. Okay. All right. Last thing I want to do is to talk about. I want to talk about when with general structures of molecules. And is we said then that when you draw the structure for a molecule, okay, each atom in the molecule has to abide by this octet rule. That means that each atom must have their 8. Okay? And like all good rules that we learn in chemistry, like all good rules that I teach you in chemistry, there's always going to be an exception. And this is going to be equally true here as well. Okay, and so with the with molecular compounds, then the exception comes in 3 different ways. First of all, with odd numbered valence electrons, molecules with an odd number of valence electrons. Okay, we will also see then the octet rule being violated, so that you have molecules in which you have atoms within that molecule will have less than the octet, and then you're going to have molecules in which the atoms in that molecule has more than the octet. So those are the 3 instances where the where we find then exceptions to the octet rule. Okay, and so with that said, we will go over this here. Okay, and take a look at let's take a look at 3 molecules in which will give you an idea of each case where you have an odd number set of electrons. You have an atom that has more than the octet, and an atom that a molecule in which an atom has less than the octet. Okay, let's take a look at whoops, sorry. Go ahead and take a look at these 3 here: nitrogen dioxide, barium, boron trifluoride, and phosphorus pentachloride. Okay, let's take a look at the first one and let's see what's going on here. Okay, so first of all, let's go ahead and let's break down the pieces here. So nitrogen then, 5 valence electrons. Oxygen then, each oxygen, and I'm going to go ahead and write it this way. Sorry. So we have 5 valence electrons here. We have then 6 valence electrons here. We have 6 valence electrons here for a grand total of 17 valence electrons. There's an odd number of electrons, folks. And do the math, and it's going to be simple math here, folks. There is no way that you can get, if every atom achieved an octet. If the nitrogen achieved an octet, oxygen achieved the octet, and both oxygens achieved their octet, you wouldn't get an odd number of electrons. That could not happen. That cannot happen. Okay. And so with that said, then when you have an odd number of electrons here, you just do your best to find then the structure. Okay. So let's go ahead and let's try this. Okay. So this is going to be trial and error again at first, folks. Okay. So I'm going to go ahead and I'm going to write it this way. Okay. Nitrogen bonds right there. I'm going to draw one oxygen on the left-hand side here. Okay, and one oxygen on the right-hand side here. Okay, all right, let's see what, hope you can see this happening here. You got the double bond forming right here. And on this end here, on the right side here, hopefully you see then that we will form then a coordinate covalent bond. So you get a single bond here as well, so that our structure then, if we draw this out, it's going to be nitrogen in the middle, single bond between the nitrogen and the oxygen on the right, a double bond then between the nitrogen and the oxygen on the left, and a single electron left over right there. Okay. So if you count this structure here, where you have a double and a single bond between the nitrogen and oxygen, you will have a grand total of 17 electrons right there. So you will have 17 electrons here. Let's count 2, 4, 6, 8, 10, 12, 14, 16, and 17. Okay. And with that said, then if you count the electrons here, you guys, if you count the electrons here, you're going to see that obviously that oxygen will have its 8. This oxygen will have its 8. This oxygen has its 8, but the nitrogen here has 2, 4, 6, 7 electrons, and there's no way around that. Okay? There's no way around that. Now, please do not add these up and say, but wait a second, Mr. N, that doesn't add up to 17. No, it shouldn't add up to 17. What we're saying here is this oxygen has its 8, this oxygen has its 8, and this nitrogen has its 7, okay, individually. But the total number of electrons, if you count it for the molecule, will be 17. So whenever you have a molecule that when you add up all the valence electrons, you end up with an odd number of valence electrons, that molecule, one atom in that molecule will not achieve its octet. Okay, one atom in that molecule will not achieve its octet. Okay, all right. Let's go ahead and let's take a look at the next molecule here. Okay, so this is an example of an odd number molecule. Okay, a molecule with an odd number of electrons. Okay, so that has to violate the octet rule. Okay, all right. Let's take a look at boron trifluoride. Okay, so boron. Let's go and do this here. Okay, we'll have this, and I will explain to you why it's not 2 and 1. Okay, and then each fluorine, and I'm just going to draw. Let's go and do this here. Well, and we have 3 of them. Okay, so therefore, then we should expect the 21 electrons here, and 3 electrons here for a grand total of 24 electrons. Okay, which seems to we look at that and say, well, wait a second, we got an even number of electrons. We should end up with a molecule that works. Okay, well, the problem here is with boron. Now, hopefully you can see then that boron has to be the center atom here. Let me move this down. Boron has to be the center atom, and I hope for obvious reasons, because fluorine can't be the center atom. If fluorine is the center atom, it can only form one bond. So it only has one lone pair, even if you try to do the coordinate covalent bonding with it. At the most, it can form 2. Okay. All right. All right, so we have that bond right there, this bond right here, and that bond right there. Okay. All right, so drawing then just the dashed model, dashed lines. You have then fluorine, fluorine, fluorine single bond. Let's draw in the lone pairs here, 3 for each fluorine. All right, so if we count the valence electrons in, each fluorine will have its 8 electrons. This fluorine has its 8 electrons. This fluorine has its 8 electrons, but boron here has 6 electrons. So the structure here then, the boron atom is going to have less than the octet. Okay? You don't have enough electrons to go around, folks, and if you count all that, you will get 24 electrons here as well. Okay? You don't have enough electrons to go around. So therefore, one of those atoms has to be deficient. It doesn't have enough. Okay? All right, so with that said, then let me go ahead and let me wrap up with the last one here. Let's see, let's start out here. We have phosphorus, and I'm sorry, up here would be 3 of those fluorines. And so for the bottom one here, let me ask you, I'm going to ask you to do this here. Okay, I would like you to draw me the structure for phosphorus pentachloride. Okay, so I will pick up with this molecule tomorrow in Friday's lecture, but I would like you to, on your paper, draw me the structure for phosphorus pentachloride and see how you can connect all 6 of those atoms into one molecule. Okay, what type of bond holds them together? How many lone pairs will you have? And then does any one of those 6 atoms violate the octet rule? Okay, so let's go ahead and get that done, and just right on time, and draw it, and let's compare our answers tomorrow, and then we'll see what you get compared to what I'll draw for you. Okay. All right. Very good, folks. I won't see you tomorrow, so I will see you on Monday. Have a good weekend. You'll see me because we'll be watching the video, but I will see you folks on Friday. If you have any questions about this material here, please stop by, stick around on Monday and get your questions answered about today's lecture and also tomorrow's lecture on Friday, tomorrow's lecture. Okay. All right. Have a good weekend, folks, and I will see you folks on Monday. Okay. Bye. Oops, hold on a second here. Sorry, let me. All right. Bye, folks.